Hello, welcome back to our course on advanced quantum mechanics. Let's see where we are now. Well, we have left classical mechanics behind, and we are now fully on the quantum mechanical side, where we have the hierarchy of abstraction looking like this. We have a Hamiltonian, which is a function of the x hat and the p hat, and possibly of t, where whenever I write just x hat or p hat, I generally mean that these could be multiple position variables and multiple momentum variables. It's just tedious to always write the indices. I will only write the indices when they will be useful. Okay, so on the top level, we have the Hamiltonian, and then we derive the equations of motion. And not only the equations of motion, we have more conditions we figured out after we came here to quantum mechanics from classical mechanics. So in particular, we do have the equations of motion. Let's just write EOM for equation of motion. And they are d by dt of x hat. Okay, now I write out the index. X hat I of t equal to 1 over I h bar, commutator of x hat of t with the Hamiltonian. And the Hamiltonian does depend on the x and the p's, but it is usual that we don't spell out that dependence in the Hamiltonian because it's understood that it's of course there. This is the equation of motion for the basic variable x hat, and then we have d by dt. Actually, let me move this. Sorry. Let me move this down here. We have the equation of motion for the momentum variable, which looks very much similar, equal to 1 over I h bar, and then the commutator of p hat with h hat. And these two together are called the Heisenberg equations of motion. And there's an I missing. Equations. In principle, we could write down the same thing for any polynomial in the x hat and the p's. But it's clear that once we know the equations of motion for the x hat and the p hat, then we have solved the basic problem here. Remember where they come from. The Heisenberg equations of motion are simply the Poisson, the Hamiltonian equations of motion, because this commutator is proportional to the Poisson bracket, and the proportionality factor is just the IH bar. So if we re-express that in terms of the Poisson bracket, where it comes from, it would simply say that the time derivative of x hat is the Poisson bracket between x hat and h hat, and the same down here. So what we found is that we have to solve the Heisenberg equations of motion next. In principle, it would seem like all we have to do now is solve these equations of motion and then climb down that hierarchy of abstraction, eventually down to a number value prediction. But we have learned to be careful going from classical mechanics to quantum mechanics, because this level of abstraction right down under the Hamiltonian actually involves more, namely also the canonical commutation relations. Let's just abbreviate them as CCRs. And we found that the canonical commutation relations are that the commutator of x hat I with, and that's as a function of time, of course, and then p hat j of t is equal to IH bar delta ij. And we have that commutator of x hat I with x hat j is 0, and so is the commutator between p hat I and p hat j. All right, we are not yet done. There is one more thing that belongs to this level of abstraction, right below the Hamiltonian, and that is the hermiticity. Namely, we want that x hat of t I dagger is equal to x hat I of t, and p hat I of t dagger is p hat I of t. We want this because we have it in classical mechanics, where this dagger here in classical mechanics is just complex conjugation. In quantum mechanics, we don't know yet what exactly this dagger means, but we know that we have to impose a condition that looks like this because we know that we have to impose the condition that whatever quantum mechanics predicts, it better be real numbers as measurement outcomes. And this fact that all measurement outcomes are real numbers, rather than complex numbers, they are real numbers, this needs to be input into the quantum mechanical framework. And that's what the hermiticity, the so-called hermiticity condition, is meant to establish. And this dagger is also called Hermitian conjugation. Even though at the moment we don't even know yet what that is going to be in practice. Just like we don't know yet what these x hat of t functions are going to look like. We only know they can't be number valued. But what are they going to be? So the situation now is that in this hierarchy of abstraction, we have that the top is the Hamiltonian. The next level down is this set of equations here. All of this is happening. Oh, it's very difficult to write on this digital pen pad because I'm writing at one place, but I'm looking on the screen at another place. That's what makes it difficult. Right, so we have now the second level of abstraction down from the top. And what we still need to establish now is all the missing levels of abstraction further down. We have to find out how we go from here further down. We don't know yet, but we do know that eventually we need number predictions for measurement outcomes. Okay, so this will this will occupy us for a little while. But in order to climb down that hierarchy of abstraction, we need to take the first step. We need to go down from here to one level further. And that level must be the level of the solutions to these differential equations. But what could these solutions even look like? What kind of mathematical objects could the x hat of t and the p hat of t actually be? We know what equations they have to obey, but we don't know yet what nature the solutions could be. We just know that can't be number valued functions. So what could they be? Now, in order to understand what they could be, in order to narrow down what they could be, let us remember something that, or let me point out something that you may not be aware of. In math, every object, and therefore every candidate for what the x hat and the p hat could be taking their values in math, every object, everything in math, can be viewed one way or the other as a map. Everything can be viewed as a map. You may wonder, what? In what sense is everything a map? How is a number a map? Well, the number 7 is a map. You can identify the number 7 as a map, namely, for example, as the map that maps everything into 7. So if need be, you can find a map describing whatever you want in math. Now, why am I saying that? Well, I'm saying that because now we know at least that we can always, if there is a representation of the x hat and the p hat that works in quantum mechanics, then it's got to be possible to express it as a number value, not as a number valued, we established that. No, it's got to be possible to describe the x hat of t and the p hat of t as being map valued. So for every point in time, we get some map. Now, does that really help to know that? Well, let's discuss that a little bit more. So maps come in two broad categories, namely maps can be linear or not, or nonlinear, or let's say not. For some maps, it doesn't even make sense to ask whether they are linear or not. So they can be linear or not. And I have good news here. We are in luck, because it turns out nature seems to allow us to use linear maps for quantum mechanics. This is huge because obviously among all maps, the non-linear maps, those that are not maps, that are not linear, far outnumber the linear ones. And among the linear ones, we have some experience. Like, we know that linear maps always map vector spaces into vector spaces. That's the nature of linear maps. That's what they do. And we've seen vector spaces before. We've seen maps of vector spaces into vector spaces before. So it's great news that for the purposes of quantum mechanics, linear maps suffice. That isn't to say that we should just relax now. Let me mention that it is an open research question whether quantum mechanics could also be done with not linear maps. Could nonlinear maps be useful here? This question has been examined every now and then over the years since the past 100 years when quantum mechanics was developed. It's been almost 100 years, right? Heisenberg discovered quantum mechanics in 1925. Every now and then it has been considered, and the most recent, or one of the most recent thorough studies of this was done by Stephen Weinberg. And he gave his best, and Weinberg is great. He tried very hard to make nonlinear maps work for solving the equations of motion and canonical commutation relations and the hermiticity condition of quantum mechanics. But didn't seem to work. There is a problem there. Not really a logical contradiction, but he just couldn't make it work. So after almost 100 years of trying, it turns out nonlinear doesn't seem to work. So it's not only that nature doesn't use it, but it just doesn't seem to work. There is no proof that I know of that says that it cannot work, but nobody has succeeded. Doesn't seem to work. Okay. So this leaves us with linear maps. Let me remind you of, just a sec, right. Let me remind you of what we are talking about. What we're talking about is the following. We go from the top level of abstraction, the Hamiltonian, one level down, where we find that we have to solve 3 conditions in order to solve a quantum mechanical problem. We have to solve the equations of motion, which, if you remember, look formally exactly the same as the classical equations of motion because they can be derived from the Poisson bracket. You don't have to derive them using the commutator as it is written here. You can derive them using the Poisson bracket, and so they are the same. Secondly, we need to solve the canonical commutation relations. That makes all the difference because now we are in completely different territory because the solutions x of t and p of t can no longer be number valued. And thirdly, we have the hermiticity condition, which is meant to ensure that later we can make real valued number predictions. Okay, so this is what we have to solve. The x of t, the p of t cannot be number valued. And now we settled on the conclusion that we should try to solve these 3 sets of equations here, equation of motion, canonical commutation relations, and hermiticity, using functions which take their values not in numbers, but in linear maps. So x of t is a linear map. For every time t, you get a different linear map. And the same for p hat of t. For every point in time, it's not a number, it's a linear map. Right? I understand that this takes some getting used to, but I'm doing this on the most abstract level with the deepest possible understanding so that when you later see the Schrödinger equation, for example, pop out of our considerations, you will see it for what it really is, what the structure behind it is, and what kind of choices went into the formulation of the Schrödinger equation. Choices you can make for representing quantum mechanics one way or the other. And not just the Schrödinger equation. I want you to understand all of the equations of quantum mechanics very deeply, and that's why we do this on this level of abstraction here. All right, so we've settled on linear maps. Now, linear maps come in different forms. It's not like there's only one kind of linear maps. Linear maps come in different forms. E.g., matrices are linear maps. Why? Well, obviously, they map column vectors into column vectors in a linear fashion. So matrices are linear maps. And that means, we can try to solve the 3 sets of conditions that we have here, namely the equations of motion, the canonical commutation relations, and the hermiticity condition. You can try to solve these with matrix. with matrix valued functions. Namely, x hat of t is then some matrix that depends on time. So it will have a matrix element x11 of t and a matrix element x12 of t and x13 of t dot dot dot. And then here it will have x21 of t and x31 of t dot dot dot, etc., etc., etc. And if you remember from the previous lecture, we should expect that these matrices may have to be infinite by infinite dimensional. Okay, and similarly, a p hat of t, which is also some matrix which will have matrix elements p11 of t, p12 of t, dot, 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 and so on. Some full matrix, all full of stuff here. Right. And these would be regular matrices with time-dependent coefficients. And by that I mean that these functions, such as x12 of t, are ordinary number-valued functions. x13 of t is an ordinary number-valued function that we have to determine. Right? And then the whole thing is a time-dependent matrix of the usual kind. So x hat of t is a time-dependent matrix, p hat of t is a time-dependent matrix. And our job then is to find those coefficient functions for the x hat of t and for p hat of t, such that the commutator between x hat of t and p hat of t is IH bar times the identity matrix. And such that the time dependence of x hat of t and p hat of t is such that the equations of motion, which happen to look just like the equations of motion of classical mechanics, are fulfilled. And the hermiticity condition tells us that it suffices if we find the solution, if we find the coefficient functions for the lower diagonal, the diagonal on the lower triangle here, because then the hermiticity condition tells us what the coefficients in the upper triangle in there have to be. Because remember that for matrices, we have that if A is a matrix, then A dagger is transpose and complex conjugate of A. And we can write this as equal to A transposed. Oh, why did I write this? Sorry. It's A. I think. Okay. It's A transposed up. Why does this not? Okay, just a sec. Sorry, the app that I'm using to write here just crashed. I had to restart it. Okay, and I lost some data here. But remember how this works? So we have that if we have A is a matrix, then the Hermitian conjugation of that matrix is, by definition, the transpose of the matrix. And then you take the complex conjugate of all its matrix elements. So that's how that works. Okay. Up. So now we have our work cut out for ourselves, right? We could just go ahead and try that. We could try to take some Hamiltonian, calculate the equations of motion, and then try to solve the equations of motion, canonical commutation relations, hermiticity condition for matrices. But before we do that, we should reconsider, because how do we know that these functions x hat of t and p hat of t should be matrix valued? Matrices are not the only linear maps. There are other linear maps. There are also other types. Of linear maps. And we don't want to bet on the wrong horse, right? We solve these matrix equations and then maybe that's not what nature does. So let's see what other linear maps are there. So, for example, let's define D to be the operation of differentiation with respect to some variable lambda. And let's define M to be the operation of multiplying with lambda. Remember why I put the double dot here? That means I'm defining something. I'm assigning a name. So this operation of differentiating with respect to lambda is now called capital D, and the operation of multiplying a function with respect to its variable is called M. Now, I'm claiming that D and M are linear maps. So first of all, how does D act? D acts in the following way. D is, when applied to a function f of lambda, is by definition, well, d by d lambda of f of lambda. Just a sec. Just checking. Yes. Okay. And what does the map M do? Well, if we apply the map M on f of lambda, well, then it is by definition the operation of multiplying our function f with its independent variable. Okay, so we have two operations here. We have D and M, and we now know how they act on functions. And these two guys are quite promising, because remember that we considered them briefly last time, and we found that the commutator between D and M is not 0. We found that it matters whether you first differentiate a function and then multiply with its variable, or you first multiply it with its variable and then differentiate. That makes a difference. It's just like showering and gymming, right? And so that's interesting, because we need maps that are linear and that don't commute. So maybe these two guys, D and M, can be useful for solving our quantum mechanical problems using linear maps. But I was just claiming, and now I should show you that indeed they are really linear maps. So notice D and M are linear maps. For example, let's check this for D. I think I'll leave it to you as an exercise to show it for M. So for D, let's see. What do we have to show to prove that D is a linear map? Well, if we apply D to the sum of two functions, then if D is really linear, then this should be the D of F plus the D of G. Well, let's check. Well, what is D of F and F plus G? Well, we have that this is equal to D by D lambda of F plus G. And this is indeed D by D lambda of F plus D by D lambda of G. So indeed true. But that's not all. In order to prove that D is indeed a linear map, we also have to show that, and we have to show that if we apply D to a number times f of lambda, so this is some element of the real, or let's say the complex numbers, then we have to check whether this is indeed the same as if we pulled out that number. By linearity, we should be able to pull out numbers, right? So this has to be D applied to f of lambda. Again, check. So what do we have? We have then that this is equal to D by D lambda of R, which is a number, times f of lambda. And we have to check whether this is equal to R times D by D. Sorry, this goes like this. D by D lambda, and then it's f of lambda. And yes, we know that we can pull this here. This is okay, and therefore, yes, it's true. So we can conclude D is a linear map. D is a linear map, and it maps functions into functions in a linear way. Now remember that functions form a vector space, because you can add two functions, you get a function. You can multiply a function with a number, you get a function. So function spaces are vector spaces, and the differential operator is a linear map. And as I said, I leave it to you to show in the exercises that M, the multiplication with lambda, is also a linear operator. So this suggests that we could try. I'm very sorry about the handwriting here. I feel like I'm a first grader here. This suggests that we can try to solve the conditions, equations of motion, canonical commutation relations, and the hermiticity in a completely different way to the matrix business up there. We can try instead to solve the equations of motion, the canonical commutation relations, and the hermiticity condition using D and M. So, e.g., we could try that x hat of t could be something like a function v1 of t, which is number valued, function of t times the d operator, times the derivative operator, plus v2 of t times the multiplication operator, and the p hat of t, maybe we can find some w1 of t and d plus w2 of t times m, and all these guys are to be number valued, right? But of course the d is not number valued, far from it. It's an operation, right? And m is an operation, so these guys are not number valued, but these prefactors could be number valued. So what we could play with is the hypothesis that there are functions v1 of t, v2 of t, w1 of t, w2 of t, such that the x hat of t and the p hat of t have just the right commutation relations and just the right equations of motion, and also the hermiticity condition such that the equation of motion and canonical commutation relations and hermiticity are fulfilled, and we solve our quantum mechanical problem. We could try this. In fact, this works. This could be done. just like above with the matrices. This could be done. Both actually work. But then, of course, we have to ask, right, it looks like work though. And before we invest all of that effort in here, we should better find out which is the right way to go. Should we find these matrix valued solutions, you know, that look like this? X hat of t is this sort of thing, and p hat of t is some matrix too? Or should we go for this kind of solution? X hat of t is some combination of the differentiation and multiplication. Actually, if we have multiple position operators here, multiple momentum variables too, then this would become more complicated, because then we have a differentiation not only with respect to one variable, but to, you know, different differentiation. Different capital D's would be needed, different capital M's would be needed for the various variables that would be involved, right? But you see the gist of it. We can do it completely differently, either with the matrices or with these multiplication differentiation operators. And you could ask, are matrices and D, M the only linear maps? Linear map possibilities? No, we are not done yet. No. There exist more options for linear maps. See how lucky we are that at least we know it's going to be linear maps, because the non-linear ones would be, you know, completely difficult, completely impossible to classify. Oh, by the way, do you know that symbol here? I hope you've all seen this. This symbol means here, this mirrored E is not accidentally a mirrored E. It's a mirrored E because it stands for there exists, like existence, right? It's an E at the beginning. And then also mathematicians, of course, use this symbol here, the for all symbol, which is an upside down A, from all. Right? Okay, I assume you've seen this. Right, so there are even more options. Now, at this point, we could throw up our hands and say, well, I don't even know where to start. Apparently, I could look for solutions among the matrix valued functions. I could look for solutions among functions that are of this form, some combinations of the D and the M operators. And now you're telling me that there are more options too. And by the way, what would be those options? Well, for example, you can use integrals. There are things called integral kernels. Integral kernels also provide linear maps. They operate differently. You know, just like differentiation is a linear operation, integration is also a linear operation. So there are options, a lot of them. What should we use? What's the right one? What did nature choose? Now, we don't have to worry that we bet on the wrong horse here, because fortunately, there is the so-called Stone and von Neumann theorem. And the Stone and von Neumann theorem, which we will cover in more detail later on, says all linear representations are ultimately the same. You can use any one you like. It's a matter of convenience. For the solution of some problems, it may be better to work with the matrices. For the solution of other problems, it may be better to use D's and M's. For the solution of yet other problems, some other representation may be better. There are just convenient and less convenient options and more convenient options, but there's no right or wrong. Because what it says is that all representations of x hat I of t and p hat j of t's, allowing that there are multiple position and momentum variables. All representations of these guys, as long as there are only finitely many of them, are the same up to a change of bases. In the vector space on which these linear maps are acting. This is great, right? Because it means, yeah, you may work with the matrices, but there is a change of bases that leads you to the representation in terms of the D's and M's. And there's a change of bases that leads you to any other linear representation that you can think of. They are all the same, just differing by change of bases. Now, at this point, you may wonder, how the heck is this possible? How can a vector space of column vectors on which matrices act be the same as a vector space of functions that you can differentiate? They seem to be more different than you could account for by a mere change of bases. Isn't it the case that when you go from a basis of column vectors to another basis, you end up with another basis of column vectors? How can you suddenly have a basis of continuous functions, differentiable functions? This is a non-trivial matter that we will cover in some detail later on. But let me give you an example. Let me remind you of an example where you've seen this thing happen before. Consider Fourier series. You have functions on an interval, continuous functions on an interval. And so these are, as I said, continuous functions. Therefore, you have a function space. You could differentiate those functions if they're differentiable, right? You can multiply them with the independent variables. That's like a representation in terms of the D and the N, right? But when you have functions on an interval, in fact, for the Fourier series, you need periodic functions on the interval. So let's look at periodic functions on an interval, so periodic boundary conditions, right? Then you can look at the Fourier series representation of such a function. And that's going to be in terms of the Fourier series coefficients, which is a discrete set of numbers which you can arrange as a column vector. You see what just happened? A continuous function on an interval can be represented by a column vector consisting of its Fourier coefficients. And this is an invertible map. You can go from those Fourier coefficients back to the continuous function on an interval. What you've really done here is change bases in your function space or in your column vector space. What we've seen here is an example of how a discrete basis for column vectors can be equivalent to a continuous basis where you have functions over a continuum. But we will address that in more detail later on, because it will be very important that we can do quantum mechanics on column vectors with matrices, or quantum mechanics on continuous wave functions, they will be called later on, which live on a continuous space and then operate with differentiation and multiplication operators. For now, all I want to say is that there is this super important Stone-von Neumann theorem, which says that the choice of whether we work with discrete or continuous representations here with D's and M's or the column vectors or any other linear representation we can come up with doesn't matter, because there's always a change of bases between them. And of course, physics has to be basis independent, right? Because it would be super weird if what nature does depends on our choice of bases in a vector space. Nature doesn't care what choices we make. And therefore, any predictions of quantum mechanics, of course, will have to be basis independent. And therefore, doesn't matter what representation we choose. Okay, so we can make our predictions in any choice of basis that we may want. All right, so let's make a choice. Let us, oh, by the way, I want to make another remark here. Our linear maps will have to work, or will have to act on vector spaces that are complex. Why? Well, because of the I in the canonical commutation relations. We just don't get away with real vector spaces because I is already in the commutation relations. So, yeah. All right. And this statement is, of course, true whatever type of linear maps we choose. Matrices, maps composed out of the D's and the M's, doesn't matter. There's going to be an I somewhere. There's going to be complex numbers involved. The vector space that we work with will have to be a complex vector space. So, for example, column vectors with complex entries, matrices with complex entries, or also the D's and the M's with functions in front of them with complex coefficients and acting on functions that are complex valued. We have to anticipate that because I is there from the start. Now, we are ready now to solve our first quantum mechanical problem. Because we know what we have to solve. We have to solve the canonical commutation relations, the equations of motion, and the hermiticity condition, and we know what tools to use now. We could use the D's and the M's, or we could use matrices. Let us start, because we have to make some choice with the matrices. They're just as useful as the other representations. And as it happens historically, the first quantum mechanical problem was solved in terms of matrices. That was Heisenberg when he had hay fever and was on an island in the Atlantic to escape the hay fever and had too much time on his hands, and then he solved the first quantum mechanical problem, which in his case was the hydrogen atom. So let's do an example here. Solve a free particle in one dimension. This is really the simplest problem one can imagine with matrices, matrix representation. Okay, so what do we have to do? We want, so we need to solve the equations of motion. And what are they? Well, remember, x hat of t, and we want to solve them with x hat of t being some matrix of t, right? Equation of motion is equal to, well, first Heisenberg equation of motion is 1 over I h bar, and then x hat of t, comma h, p hat of t equal to 1 over I h bar, and then we have p hat of t with h, and then, well, for h is equal to, or h hat is equal to, well, free particle in one dimension, that's p hat squared over 2m, right? Okay, let's do this. That's the Heisenberg equation of motion. Well, let's solve this first one. What do we have? We have that x hat of t is equal to 1 over IH bar. And it's going to be a little bit tedious, but let's do it once. So we have x hat, and I'm dropping the t here. We know it's going to be time dependent. X hat, and the p is p hat squared over 2m minus, and then we have, I should really put this in front, p hat squared x hat, right? Because this is the commutator. I'm just writing out what the commutator is between x hat and h hat. So that's the commutator there. So we can write this as being 1 over IH bar 2m. And then x hat, p hat minus p hat, x hat. Now, recall, we have x hat, p hat minus p hat, x hat is equal to IH bar. So therefore, we can write this as being equal to 1 over IH bar 2m. And then let us try to process this so that it becomes a little bit easier by using the canonical commutation relations. So what we do is we commute the x and the p here, because then we will get the term pxp. And we can do the same thing over here. If we use the commutation relations for this term, then we get a term xp. So we also here get a term pxp. That's great, because we had here then a term pxp and here a term pxp. They can cancel each other out, and you only need to worry about the remainder. Why is this always going to work? Tell you why. Remember when we used the Poisson bracket to evaluate equations of motion in classical mechanics, or in quantum mechanics? When we use the Poisson bracket, there is this Poisson bracket rule that allows us to reduce the degree of a polynomial, right? This is what always works with the Poisson bracket, and the commutator is just the representation of the Poisson bracket. So it's got to work here as well, and it does. Let's have a look at how this works. So the xp, what happened here? The xp term here, I wanted to take this one away, that one away. Okay, so let's look at this term xp. This becomes p hat x hat minus IH bar. No, plus IH bar, right? Because x hat p hat is equal to IH bar plus p hat x hat. So it's this term here is this term here, right? So we have this times p hat minus, and then we have here p hat, and then what is p hat x hat? Well, let's look at the canonical commutation relation. P hat x hat is x hat p hat minus IH bar. So it's x hat p hat minus IH bar. Okay, so this term here is equal to that term here. And now we can close the big bracket. So what is this? This is 1 over IH bar 2m. And then simplifications. You see, this term, let me just delete this one. This term, this term cancels that term, right? Because both of them are p hat, x hat, p hat. P hat, x hat, p hat. Goes away. And we are left with what? With IH bar p hat plus IH bar p hat. So what we are left with is 2 IH bar p hat. Now that's very welcome, because we can now cancel this 2 IH bar with this IH bar 2. So what we end up with is the answer, namely that x hat of t it's d by dt, of course, of that, right? We are writing down the equation of motion, of course. Oof. Right, d by dt, and here too, d by dt of x hat of t is equal to p hat divided by m. That sounds an awful lot. It looks like an awful lot like the time derivative of the position is the velocity, huh? Because if you divide the momentum by the mass, you get the velocity. So what we observe is this looks very familiar. It looks like what you would expect for a free particle in classical mechanics, and there's no h bar in this. So why did we go through all of this trouble here in order to arrive here? And the answer is yes, indeed, we would not have had to go through this trouble. I just wanted to show you once how it works if you want to do it. But of course, we could have jumped straight to this because we know from all the abstract work that we did in the first few lectures that the equations of motion of quantum mechanics are the same as in classical mechanics. These are the equations of motion. This is an equation of motion of classical mechanics. You get the one for quantum mechanics, but just putting hats on stuff, right? So we just saw this work out again. And then, of course, we also have, and we won't do that in a tedious way. The answer is easy. We have that, oh, it's d by dt up here, right? We also have that d by dt of p hat of t is equal to, now let's see, what do we have here? It is 1 over IH bar. I am, in case you can't see my cursor, let me just circle that. We are here now. Okay, so if we want to evaluate what this commutator is, well, what is it? It's a commutator between p hat and p hat squared. But of course, p hat is commuting with p hat. It's the same thing, right? So clearly the right-hand side is 0. And again, we should not be surprised about this because, of course, in classical mechanics, the momentum doesn't change either for a free particle. It's not exposed to any forces, so its momentum stays constant. All right, so what we have recovered here is something we could have guessed from the beginning, but I still felt it good to show you exactly how it works out if you want to do it. The equations of motion that we need to solve are these, right? Oh, it's so difficult to draw on this pad, at least while I'm not yet used to it. Okay, so this part is the equation of motion part. What we have to do is find matrices, time-dependent matrices, x hat of t and p hat of t, that obey these conditions here. All right? Good. But we also have to solve so also we need to solve the canonical commutation relation. So this is one dimension. So we also need to solve x hat of t, p hat of t, equal to IH bar times the identity matrix for all t. And let me spell this out. This is the identity matrix, identity matrix. Because we have decided to look for solutions among the linear maps which are matrices. And for matrices, the identity is the identity matrix. So we have to solve this and also need that we find matrices x hat of t and p hat of t which obey that x hat of t Hermitian conjugate, which means transpose complex conjugate, is equal to x hat of t and p hat of t dagger is equal to p hat of t. Now, at this point, you might say this is a tall order, right? How do we solve the equations of motion, the canonical commutation relations, and the hermiticity. With matrix-valued functions. And remember also, we anticipate that these matrices will have to have infinitely many entries. It looks like we have infinitely many problems to solve here, and in principle the answer is yes. However, we already did last time in the previous lecture much of the work that we need to do here. Namely, recall this useful fact from the previous lecture. You know, if you want to experience what I'm experiencing, try to write with your eyes closed and then look at how it looks like. This is how it is to me, because I'm writing here on this pad while I'm looking at the screen. So I don't look where I'm writing, and that makes it really hard. It's like blind writing. But I suppose it's learnable. All right, so recall the following useful fact from the previous lecture, namely, we were using the following type of matrix, if you remember, zeros on the diagonal, and then we had here square root of 1, square root of 2, square root of 3, etc., and then zeros everywhere here, zeros everywhere there. Let's give this thing a name. Last lecture I didn't give it a name, but it's convenient to give it a name. Let's give this matrix the name A. Okay, so it has zeros on the diagonal, and then just next to the diagonal, it has square root of 1, square root of 2, square root of 3, etc. And the rest of the matrix is 0, 2. Now, what is the Hermitian conjugate of that matrix? Well, the Hermitian conjugate of that matrix is the transpose complex conjugate. Now, there's nothing complex in here, so we can forget about the complex conjugation, it's trivial. But there is transposition that needs to be done. So what do we get? Well, if we transpose that matrix, then it will be this matrix, square root of 1, square root of 2, square root of 3, etc. And zeros here, zeros there. Okay. Then we found that if we define a matrix that we may call x hat of t naught, just a name, if we define this matrix as L, where this is some, this is some real number, arbitrary constant. Okay, L times A dagger plus A. If you look back at the previous lecture, I just put all of this into one matrix right away. And this lecture now, I'm just decomposing it into the A and A dagger. Right? And if we define this, and then we also define the p hat of T naught to be I h bar divided by 2L A dagger minus A, then we found that x hat, well, finding is a little bit much. I was claiming it to you and left it to you to prove it. But you will find it's true. We then find that this is true. Could do IH bar, the identity matrix. You see, to prove this is something completely pedestrian. You just take this x hat of T naught, which is defined as L times the sum of these two matrices. So it's some big matrix with infinitely many entries, but a very explicit concrete matrix. And then you take the p hat, which again, by these instructions, is a very explicit concrete matrix with, yes, infinite by infinite matrix elements, but very concrete. And then you multiply them. which is a little bit tedious, admittedly, but once in one's life as a physicist, you have to do this. So you multiply these two guys and then multiply them the other way around, take the difference between the two and discover that, yes, it's IH bar times the identity matrix. In other words, this means the canonical commutation relations, or it's singular, it's just canonical commutation relation, is okay at t equal t naught. You see, what we've just done at this moment is actually something super cool. We have, by writing down x hat of t naught as this matrix and p hat of t naught as that matrix, we have indeed solved the quantum mechanical problem, at least for some point in time that we may choose to be the initial time where we start our solution. So what we have found is a solution for time t naught. We have not solved the dynamics yet, but we have solved at one point what it is. We have solved the canonical commutation relations at once, except there's a catch. We still have to check the hermiticity condition. So check hermiticity. So is it true that x hat of t naught dagger is equal to x hat of t naught? Well, yes, because indeed L, a dagger plus a, and then you take the dagger of this, is equal to, well, L star, because L is a number, remember? And then we have here a plus a dagger, okay? But what is this? This is L because we wisely chose our L to be a real number. So it's L times, well, you can also write this as a dagger plus a, right? And so therefore, yes. And similarly, you can check that also p hat of t naught is Hermitian, that it obeys the hermiticity condition, because, let's just quickly check. Actually, I'm not sure. Maybe I was putting this as an exercise. Am I solving your exercise now? I might be. Okay, so I won't do it. But you can see how this is to be checked, that p hat, so p hat of t naught dagger is equal to p hat of t naught, right? You can check that too. It's a little bit of a proof going on here. All right, so we are almost done solving our first quantum mechanical problem from scratch. Namely, we've solved the canonical commutation relation, we've solved the hermiticity condition, but we haven't solved the dynamics yet. So we still need to solve. We still need to find x hat and p hat, not only for the initial time, we need to find this x hat of t time-dependent matrix and p hat of t time-dependent matrix. So still need to solve the equations of motion, which are that x hat of t d by dt is equal to 1 over m p hat of t, and that d by dt of p hat of t is 0. Remember, these were our equations of motion. Luckily for us, they can be solved. It's not too hard in this case, and that's nice because we just want to get familiar with how to do this in principle. We don't want to solve the most complicated case at once. So this is easy to solve, right? This equation of motion we start with, because what we find is that p hat of t equal to p hat of t naught fits the bill, right? Because, yeah, what this equation of motion is saying is that the momentum matrix doesn't change in time. Okay, fine. So we've already solved this part here. This is great, isn't it? Because now, from this, we can tell that the equation of motion for the position matrix now reads d by dt of x hat of t is equal to 1 over m, and then it's p hat of t naught. This is a constant matrix. So this makes it easy. From that we know that x hat of t is equal to, well, x hat of t naught, we need this to fulfill the initial condition, plus t minus t naught, again, a factor needed for the initial condition, times 1 over m, and then p hat of t naught. Right? Because if you do this, what do we have? We have that at time t equal t naught, the second term goes away, and we have the initial condition is fulfilled. X hat of t is x hat of t naught. And at some other time, the derivative of x hat of t is what? Well, the first term goes away because it's constant in time, and the second term contains a t in it, and we differentiate that, the t goes away, and we just have p hat over m, so it's fine, it's also obeyed. So this means we now have solved our first quantum mechanical problem. So we have x hat of t and p hat of t as explicit explicit matrices, matrix valued functions. Namely, we have, here it is, this is an explicit matrix valued function of time because x hat of t naught is expressed in terms of a and a dagger, which are expressed explicitly as matrices. And here the p hat of t naught is 2. That 2 here is represented explicitly as a matrix in terms of the a and the a daggers, right? And the p hat is an explicit matrix, namely the p hat of t naught, and it doesn't even have time dependence. So what we have is that we, in our hierarchy of abstraction, went down one step. These two equations in the yellow boxes are the following. If we go back to the very beginning of today, we had on the top level of abstraction, we had here, we had the Hamiltonian, right? And then the next level of abstraction is this one, where we have this set of differential equations, the canonical commutation relations, and the Matrices condition. And now, where there used to be a question mark, we have the next step, which is, we have here, we can erase that question mark now, and we can write here, matrix valued solution functions, x hat of t and p hat of t, which are matrices, right? Dot, 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 and dot, 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 dot. What remains to be done is, of course, that we continue climbing down the hierarchy of abstractions so that we, at the bottom level, arrive at number-valued predictions. This is what we will need next. We will need to find out what is going on here. How do we do this? How do we climb down from matrix-valued solution functions to number predictions so that we can tell the experimenter, I think you're going to get this momentum or that position and so on. So this is what we're going to do next. I'll see you then next week. Have a nice weekend.